So this is problem number 11. It's from the 2012 AP Calc exam. Non-calculator question. The question ultimately is, which of the following statements is true? And if you glance down through some of these, they involve continuity, differentiability, limits. Uh, but the function that we're asked this question about is a function that I don't really like in its current form. It's a square root, so that's okay, but then under the square root we have absolute values of x minus 2. What my personal preference is, and I'm thinking a lot of yours would be as well, when you have absolute values, it's usually a little more convenient to redefine your function in a piecewise form. So I have that done right down here, but I want to make sure you understand how I accomplish that. So absolute values do absolutely nothing if what's inside of them is 0 or positive. They serve no purpose. You can just get rid of them. So I wanted to know when what was inside the absolute values is 0 or positive. When is it greater than or equal to 0? And I figured out that that's when x is greater than or equal to 2. So when x is greater than or equal to 2, I basically just drop the absolute values. They serve no purpose when what's inside of them is positive, so what's the sense in having them there in the first place? They do something, though, when this inequality is not true. Because if this is not greater than or equal to 0, it's less than 0, and the absolute values are going to take that quantity, x minus 2, and they're going to change it to a positive value. So the quantity is initially negative because it's less than 0. The absolute values change that negative to a positive. A way that we can manually do that without having the absolute value stick around would be if we dropped the absolute values but negated the quantity that we already know is going to be negative, because x being less than 2 makes x minus 2 negative. So we're doing the job that the absolute values do, change the negative to a positive, with this sign rather than leaving the absolute values there. Usually it's a little more convenient to have the function re-expressed like this when you're trying to reason out questions about limits, differentiability, things of that nature, which is exactly what we're trying to do here. So I saw a lot of these involved continuity, and I know this one involves a limit. So what I wanted to do right away is check my limit as I approach 2. So on the bigger side of 2, I'd satisfy this inequality. And on the bigger side of 2, I get the square root of a positive that is going to exist, and the square root of 0 is going to be 0. So on the bigger side of 2, our limit is 0. On the smaller side of 2, little uglier to reason this out. So if I take a number a little bit smaller than 2 and I subtract 2 from it, so this is not 2 minus negative 2, this is a number slightly smaller than 2, denoted right here, so like 1.9 minus 2, that gets me close to 0, but it leaves me on the underside of 0. Now that would normally be an issue underneath the square root, but when we're on the smaller side of 2, we'd be satisfying this inequality statement, so we have this negative sign that's going to take that number that's slightly negative and turn it into a positive. And once again, the square root of a number that's tiny and positive is going to be approaching 0. So the limit does exist. The limit equals 0, so we can safely rule out choice D since that statement is true. If you look at this statement here, f is not continuous at x equals 2. The limit exists as we approach 2. The limit is equal to 0. The function value at 2, 2 minus 2, is 0. Absolute value of 0, 0. Square root is 0, 0. The function value and the limit equal the same thing, so we can also say that since the limit and the function value are equal, the function is continuous, so statement C is not true. F is continuous but not differentiable at 2. F is differentiable at 2. These ones look similar to each other, so I think I want to tackle those next. So what I did is I took the derivative of both portions of this function, right? So over here I have f prime of x, and I do have it in a piecewise form. So I did need to think about the root as a 1/2 power, so I multiplied by the 1/2 power, subtracted 1 from it, left the inner function there, finished off a little chain rule. That's only the derivative if x is greater than 2. I haven't included 2 on this interval because what happens a lot of the time with piecewise functions, even if they're continuous, at the transitional x value, which is definitely the case here, you still might have a cusp there. So I don't want to include 2 on this interval because then I'm implying that the derivative has a value at 2. I'm investigating what's going on over here in order to make that determination right now. When I'm looking at this piece of the function, once again, I think of the root as 1/2 power, so I multiply by the 1/2, subtract 1 from it. I leave the inner function inside of this. Now, with the inner function, I distributed my negative in, right? So I have negative x plus 2 rather than the way you see it represented over here. And then, since I am in a chain rule situation, I have to multiply by the derivative of the inner function, which is negative 1 for this inner function. And that's the derivatives if x is less than 2. So if the derivative exists at 2, I would need the limit as I approach 2 on the bigger side of the derivative to equal the limit as I approach 2 on the smaller side of the derivative. If these two expressions don't equal each other at the x value of 2, I have a drastic change in slope at that value of x, at the x value of 2, and therefore I'm not differentiable. So I went ahead and I checked the limit as I approach 2 from the bigger side. So bigger side of 2 satisfies this inequality. I noticed that I had this negative power here, so I bumped that to the denominator, made it back into a root since it would have been a positive 1/2 power in the denominator. And then if I put a number slightly bigger than 2 in, minus 2, I get a small positive, just like we talked about over here. If I have 2 times a small positive, I'm looking at a small positive still in the denominator, and 1 divided by a really, really tiny positive value, 1 divided by 1/1,000,000th is 1 times 1,000,000 over 1 multiplied by the reciprocal, and that's a big value in the end. So on the bigger side of 2, the slope of the tangent line, the value of the derivative, is going to get really, really steep, and it's going to be positive. On the smaller side of 2, I did something similar, so I'm checking the limit as I approach 2 on the smaller side by analyzing this portion of the derivative. And when I take a number that's slightly smaller than 2, like 1.9, and I put 1.9 here, I end up with negative 1.9 plus 2. Well, that gives me a tiny positive value. I still have to multiply that tiny positive value by the 2 that was already in the denominator because of this 1/2 here, after doing that square root, of course. And I still get a small positive in the denominator. But because of the chain rule being different for this portion of the derivative than it was for this portion of the derivative, I actually have a negative 1 in the numerator here. So when I have negative 1 divided by a tiny positive value, negative 1 divided by 1/1,000,000th, we'll multiply negative 1 by the reciprocal, multiply it by 1,000,000 over 1. You get negative 1,000,000 then. This limit is going to tend to negative infinity. So the slope of the tangent line, the derivative value for values of x slightly smaller than 2 on this function, they are really, really steep, but they're really, really negative. We definitely don't have the same slope on the two sides of 2. These are about as extreme opposites as you can have. Therefore, f prime of 2 is something that's not going to be defined. So the function is continuous. Yes, we've already checked that box. We ruled out C a little while ago, but not differentiable. We've just confirmed that. So we are looking at choice A. Choice B is ruled out because we've just said it's not differentiable at 2. X equals 2 is a vertical asymptote of the graph. It's kind of the oddball here. It doesn't really relate to any of the other pieces, but you can quickly kind of realize that one's not true because the function's defined at 2. Right, 2 minus 2 is 0, absolute value of 0 is 0, square root of 0 is 0. You don't have something undefined at 2, your function is defined there, so there's no way you can have an asymptote where your function's defined.